since I've heard his talk in the practice run. He's really talented in bringing some of that big stuff of the universe down to common folks' understanding. So let me, please join me in welcoming Chris Jacobs.
Handing the mic in? There you go. Okay. Good.
Yes, the idea is to put it in first, then turn it on. So even PhDs can learn. Okay, the first thing I want to say is what this lecture is.
Is that mic on?
Yes. Okay.
I'm afraid to turn it up anymore because of feedback.
Let me just put it like this. The first thing I want to mention is that, well, first of all, is there anybody, everybody here? Okay. We're not going to go into deep physics. We're not going to go into naming all the stars because most of those, it's all Greek, literally. Most of the names are Greek and Roman and so on. What we are going to talk about is some of the realities of the universe, real stuff that happens all the time, and Earth, calm down, everything nice and quiet, have no appreciation of it unless you read it, unless you hear about it, unless somebody tells you about it. It's not a class in physics. We're not going to try to make physicists out of you tonight. And I've taken the liberty of rounding things off for simplicity. For example, a light year, which is the amount of time that very speedy light travels, is really 5.9638 trillion miles. We're going to call it 6. That's it. 6. Close enough. Because you'll lose it in the details. And again, what I'm trying to show is our position in the universe, where we fit in with everything else compared to what's going on. Now, much of what is really large for us, really big, really powerful, really neat, is so infinitesimal that it is humbling. It teaches us, and depending on your diversification and how you look at it, it teaches us there's a greater force that's acting out there. It teaches us where we fit in the position of things. And it's very inspirational. It shouldn't be humbling exactly. It should be more inspirational in that we have so much we can do and so far we can go. Okay, next slide, Jan. Yeah. Now, I hope you can still hear me. I'm going to make the talk mostly about things that you know a lot about or you've heard a lot about, like black holes, less people on superstrings, quantum mechanics, relativity, but very few people have heard about M-theory. So we're not going to talk a lot about M-theory tonight. I just want you to have a feeling when you hear these terms going on and on, to know what they are. Okay, now, for example, I'm going to ask, I can see better than I thought. How many of you have heard of the term black holes? Oh, almost all of you. Okay. Well, first of all, we think of a black hole as something big and massive. And we're going to get into show you that there are black holes the size of an atom. Just one atom. It's incredibly small. You've all heard, I'm sure, of E equals mc squared. That's Einstein's law. But there's some things I want you to keep in mind as this lecture goes on, and that is the energy, the destructive energy of motion, the thing that happens in a car crash, the thing that happens when a rifle bullet hits something, goes up as the square of the speed. Double the speed, you don't have double the kinetic energy. Double the speed, you have 4 times the kinetic energy. And that's going to be important in a minute when we'll talk about that. Another thing is the speeds that we deal with and the shortness of time. Has anybody here not heard of the term nanosecond? Okay. Nanosecond is 1,000th of 1/1,000,000th of a second. And things happen in the universe in nanoseconds. In other words, you take a second, you slice it into 1,000,000 pieces. You take one of those pieces, you slice it into 1,000 pieces. You take one of those pieces out, you've got a nanosecond. The title of the talk is Proportions and Ratios of the Universe. 1 nanosecond is to 1 second, as 1 second is to 30 years. And things take place in the universe so fast that they are sub-nanoseconds, in fractions of a nanosecond. Now, we as humans, up till about 1900, got around to thinking that we sort of knew the laws of physics. We knew what was going on. We understood everything. And then along came this guy about 1905, and he was a real troublemaker. Boy, did he stir things up and cause people to lose all their confidence that they understood the mechanics of the universe. Anybody care to guess who that guy was in 1905? Exactly. Change the tape. That's the troublemaker. Did you know that before Einstein explained how gravity distorted space, it distorts space, it bends it like a rubber band. Before he explained it, people thought that Mercury, our closest planet to the sun that went around, was actually, their instruments in measuring its orbit were wrong. They looked at it and they recalibrated and they couldn't believe it because it did not move the way every single law of physics up to that time said it should move. It didn't return to the same space. The orbit wasn't consistent. People were absolutely stunned, and their only answer at that time was to say that their instruments were wrong. Now, when I say that Einstein brought to our attention that space was bent, what that means is if you were on a curved road, but it was so well banked that you couldn't tell that you were turning, that's what gravity does to space. Okay? It bends it in the way a curved road is bent by banking, preventing you from knowing that it's there. This is the background of how we got into what we understand today about the universe. And some of the examples of what we as humans think is significant is so very small in the overall scheme of things. Let me give you an example, and some of you may have already known this. There are billions of stars in the Milky Way. This is our galaxy. Galaxy is a cluster of stars, and in our galaxy, the Milky Way, there are billions of stars. Now, that's pretty impressive until you realize there are billions of galaxies. So, I don't know if you remember, and people made fun of Carl Sagan, but computationally, he was right. There are more stars in the universe, known universe, and who knows what's beyond what we can see. There are more stars in the known universe than there are grains of sand. He was the guy that said billions and billions, you know, the number of stars in the known universe. He probably also said the amount of my last royalty check, but I don't know about that. I wasn't there when I watched him cash him, but no, he was right computationally. So there are more stars in the universe than there are, and it shows where we fit in. We are a minor star on a minor arm. The galaxies come out like spokes on a wheel in a minor universe. So when we start to think that perhaps we're the center of everything, maybe we should relax a little and not worry about it so much, because we're not. So we're not responsible for the whole thing. We're just one grain of sand on the entire universe. Let me give you an example of our efforts compared to outside. Here's a pretty good example, I think. About 10 years ago, they discovered and then sent a probe to look at a small asteroid, Ida. Going around this small asteroid was a tiny little moon, very small by space standards. It was mostly made of nickel and other non-ferrous materials. Well, it turns out that that small moon on a small asteroid is more metal than humans have mined since we started mining. Total that we've ever mined. It shows you the proportion of how small our efforts are compared to things that are relatively tiny in the universe. Another example that we're finding out more and more about now is a thing called neutrinos. Neutrinos, who's heard of the word neutrinos before? Neutrinos are the smallest particle that's a real particle, not a figment, not a string, that's a real traceable particle. Every second of our lives, over 100 billion neutrinos pass through every square inch of our body. These neutrinos are so energetic and so powerful, they could go through 100 light years of rock, pure granite, and not slow down. There's some evidence that what happens is these neutrinos knock carbon particles and other elements off our cells, and they are related to the aging process. They are one of the reasons that aging seems to be beyond our control, and that is these neutrinos are coming in and knocking bits off our cell structure, so that when the cells reproduce, they don't quite reproduce anymore. More stuff is going on in the universe than we could ever imagine so far. In fact, the universe isn't stranger than we can imagine. Some people say it's stranger than we can imagine. Okay, the third part of this lecture, we've done background and we've done quantities, is sizes. How big are we compared to other things? Let's get some Milky Way facts up there. And again, I'm going to come around and show it with the laser. This is our Milky Way, one of billions of others. The diameter of the Milky Way is 100,000 light years. So, if it's 6 trillion miles to a light year, it's 100,000 times 6 trillion miles across. You'd have to get awful good mileage to drive that far. The thickness of the disk, and it is a disk, is 2,000 light years. The distance of our sun from the center, see, we're a quarter of the way out. That's where we are. The number of stars is at least 2 billion. And the time for the sun, and remember, these stars rotate about the center, is 200 million years. The reason that time frame is important is because it gives you an idea of how difficult it is for us as humans to comprehend something that lasts, and one revolution takes so much longer than we can last. Now, to put some of these perhaps more into proportion, there are, the biggest planet is what? Jupiter. 1,000 Earths can fit into one Jupiter. 1,000 Earths can fit into one Jupiter and be totally swallowed by Jupiter. 1,000 Jupiters can be swallowed up by our sun. And 1,000 of our suns, we're a relatively small star, 1,000 of our suns, not the biggest star, but a relatively bigger star, 1,000 of our suns will go into it. So we are not as a planet, we're not a dynamic force in the scheme of things. And again, that's a proportion of the universe. Now, I'd like to look at speeds. How fast are things? This is the next, and distances. We've done sizes, let's do distances, and then we'll do speeds. Okay, let's have the distances. And you notice I've made a differentiation between speeds and distances. Okay, here's the speed. Nothing is faster than light. Light travels in a year 5.865, call it 6 trillion miles. Our solar system, from one end to the other, would take light 0.13 years to cross. The nearest galaxy that Gene was talking about before is 2.2 million light years away. It gives you a feel. If it only takes light 0.13 to go farther than any space probe that we have ever done, really, although we're now getting a little bit out, so give us credit to 0.2 maybe, the nearest galaxy is 2.2 million. They're mature galaxies. Now, what they say mature means that it has taken light 5 billion years to reach us. So they're pretty mature. This is what they looked like 5 billion years ago. And baby galaxies that were in their infancy, 11 billion light years. And then there's the dark zone. And we'll explain a little bit about the dark zone later. For the proponents of the Big Bang, that when they project backwards, 14 billion years ago is how long it took for from the Big Bang to now. All right, let's talk about accuracy and distances and where we're going. If you took the fastest thing that humans have ever done, about 3,000 miles an hour, you'd say, that's pretty quick, you know? That's getting up there in speed. And I'm going to explain about this later. That's cheating. That is using what's called the slingshot effect. And I'll explain the slingshot effect in a little bit. Let's look at the accuracy that it would take. Well, first of all, let's talk about how long it would take to reach a star at the fastest we have ever achieved as humans, and the closest star to us, which is about 4.3 light years away. Does anybody want to take a guess as to how long it would take to reach that star? At the fastest we have ever shot anything. The answer is 27,000 years. At the fastest we have ever made anything travel. 27,000 years. So much for Star Trek in at least the immediate future. And that's cheating. Remember, that's using the planet's slingshot. That's the accuracy we would need. It is the equivalent. If you want to hit that star, not a bullseye, but anywhere on that star, it would be equivalent as a ratio to shooting a rifle bullet from Midland to New York City, accurate within 3 inches. That's a good aim. That's the type of accuracy, again, it's not something that's in our technology at present. If you wanted to hit something the size of the Earth going around one of those stars, it would be to within 0.025, 25 thousandths of an inch. That means about the diameter of the wire in a paper clip. So you would have to be able to shoot something from Midland to New York and hit within the diameter of a the wire of a paper clip. That is way beyond our capability. Okay, that gives you a general idea about the distances. But now I'd like to deal with something else, and that is density. Density is different from weight. In other words, a pound of feathers and a pound of lead weigh the same. Density means how much weight you can pack into a small volume. Now, here's one of the most interesting things that I have run across, and that is how open solid matter is, how very, very open it is. For example, if you took an atom and you made the nucleus, the center, the size of this tennis ball, then the electron that goes around, and we all sort of learned that the electrons go around the center of the atoms, but we didn't learn where they went around. If you made an atom the size of this tennis ball, the electron would orbit the atom. It would be about the size of a pinhead, and it would orbit the atom at 75 miles. Everything in between is open. Everything is open in between. As incredible as lead, steel, granite, everything is, that's how open it is. And since the gravitational forces inside a star are so massive, so incredibly strong, and we'll get into forces, you'd say, well, darn, why doesn't it just crush it all and put it together into one big massive block? And the reason is that as it collapses all this matter, mostly hydrogen, it literally forces two hydrogen atoms to combine into a helium atom. What is released when you do that? A little bit of energy, a little bit of matter is converted into a lot of energy. How does that energy show up? It shows up as little packets that come flying out from the combined area, and they come whizzing out from that combination. Even if when we slam them together in the lab, we still get that flying out of photons mostly. And what happens as gravity tries to bring these hydrogen atoms together into one massive block, the photons come flying out and prevent the collapse. So that light and heat is what makes the stars shine. It is not what heats the stars up, believe it or not. What heats the stars up is gravity. The combining of the hydrogen into helium cools the star. Now that's an amazing thing. It's what shines and warms our planet up is not the heating of the sun. It's the photons flying out that is preventing gravity from overheating the sun, and it's literally cooling the sun. So yes, it's still over 100 in Midland today, but that doesn't change that at all. But it still explains how this star can shine so brightly and be so hot, and yet it's actually colder than it would be. I mean, it's colder than it would be once the fuel runs out, and we'll get into that. What happens when the fuel runs out? Well, once the fuel runs out, then the collapsing process begins, and that's when things really get hot. Let's see how. And remember how loose matter is, even though it's granite and steel. Remember how it collapses down, and gravity would pull it all together and crush the electrons right into the source of the nucleus if it weren't for the hydrogen converting to helium. But eventually, all that hydrogen runs out, the helium runs out, and it's just inert. And the most inert of all materials is iron. And it winds up becoming a glowing ball of iron. And even that is crushed in. So change the slide. I'd like to show proportions here. This is the scale of things. When the sun becomes a white dwarf, that means made out of just iron. collapse. Right now, it's 870,000 miles across. It'll pack down to the size of 7,500 miles, which is about the size of our Earth. When it even collapses more than that, a star that starts out 1.5 times as big as our sun will collapse down to 15 miles. That's all. 15 miles across, about the size of Manhattan. As a black hole, a star 30 times our sun, which is what it takes to make a black hole in space, will have a diameter of just a few miles. So let's look at this. Here's a segment of our sun. When it shrinks, this is how big our sun is going to be compared to our sun now. This is how big it will be when it becomes a white dwarf, when all the hydrogen and all the fuel is used up. Now, part of the white dwarf, this is a very big white dwarf. As it collapses, that's how big it'll be when it becomes a neutron star. This white dwarf down here becomes a neutron star. And part of a neutron star, compared to a black hole, and most of you did put your hand up and say you knew about black holes, part of a neutron star becomes that big. So from this to this to this to this to this to that, that shows you the total proportion of how tiny, how dense, incredibly dense this is going to be. Now, what does it take? How much gravity does it take to make this happen? A white dwarf is a small star. It's like iron. It'll become iron. It's about the size of our sun. A medium star is a neutron star. And that's about 3 to 5 times as big as our sun. So if it started as our sun, it'll become a neutron star like that. When you get up to and there are many stars this big, when you get up to a star that's 30 suns, then you go to a black hole. And we're going to talk about black holes in a way that I don't think you've seen before. Now, how dense is some of this material? Well, let's have the next slide. A matchbook from a white dwarf would weigh as much as an elephant. Okay, that's how dense it would be. So if I had a matchbook size of a white dwarf on this table, of course it would just crush everything down. And it would weigh about 10,000 pounds. Further going on, let's have the next slide. How about the next one down, if you remember, was a neutron star. A head of a pin on a neutron star would weigh as much as 2 super tankers. If you had a neutron star here on a pinhead of it, there'd be nothing that could stop it from going straight down to the center of the Earth. It's the second most incredibly dense material there is. So the sun as a neutron star would shrink down to a mile, about a mile across. Now, up above that is what's called a black hole. A black hole crushes everything out of existence. Literally, it crushes it out of existence. It just doesn't. The material, and there's a saying that says black holes have no hair. And the reason for that is any characteristic of anything that goes into a black hole is lost forever. It's permanently destroyed. There's only 3 things that will determine every black hole. One is its mass, of course, how much density, how much mass is in there. The other is the electrical charge on it. And the third thing is how fast it's spinning. That's it. There is no other characteristic. Everything else is obliterated in a black hole. Now, there are some supermassive black holes out there that are slightly smaller than our entire galaxy. Smaller than our galaxy. They weigh more, they are so dense, they weigh more than our entire Milky Way. And that's documented. They have gravitational effects that they can see through the Hubble telescope, where they just, there'll be a star will just come hippie-hopping along, a whole star, bigger than our sun, and it just and it'll suck it up like a big vacuum cleaner, and it's gone. That's how massive there are some black holes out there. Now, how dense? You know, we talked about the supertanker as a pinhead for a neutron star. How dense is a black hole? Okay, nobody knows, because as I said, once it goes in there, it's gone. What we do know is how big what they call the event horizon is. The event horizon says that anything that gets closer than that, even light can't escape. It's a trap. Once you cross that trap into the event horizon, there are no more events underneath that, because everything goes in and disappears. Now, earlier in the lecture, I said that you could always make a black hole. If you exert enough pressure on anything, you could make a black hole. I mean, it would be a good science fiction article about a guy that wanted to end it all and end Earth too, and he started a black hole by some tremendous pressure with just a size of an atom on Earth, and he could find a way to exert that kind of pressure to crush things down at. Well, once that happened, it would just shoot right to the center of our Earth and pull everything else in with it. And once that happened, our entire Earth, everything that we know, would be crushed down to, go ahead and change the slide, to 1 inch. That's how big our Earth would be were it as dense as a black hole. The event horizon would be 1 inch. There are forces out there that are just so strong, so much stronger than anything we have ever seen, that it's almost beyond our comprehension. Now, I'm going to take, before we go to speeds, and this is what I told you, we're going to define a new way to look at a black hole. Does anybody have any questions? Anything that I could answer right now, or comments? No? Okay. Well, we're going to speed on to speeds then. One of the fastest rifle bullets, for those of you that know bullets, commercial bullets, is the 220 Swift. 220 Swift exits the muzzle of a gun at about 7/8 of a mile a second. Not a minute, 7/8 of a mile in 1 second. It hits with tremendous devastating force, tremendous force. It just opens things up. You'd say, wow, man has really gotten somewhere. 7/8 of a mile a second, that's a terrific speed. Well, until you realize that just to make it around the sun in a year, Earth has to move at 18 miles a second. So we're zipping through space at 18 miles a second compared to a 220 Swift, which is 7/8 of a mile a second. The fastest man has ever achieved is way under that speed, way under 18 miles a second. Now, I said we're talking about speeds and how Earth can, or how we can achieve the speeds that we do with the slingshot effect. I had always wondered, until it was explained to me, as a rocket is drawn into the gravitational field, like let's say of Jupiter, of course it would go faster. It's coming and plunging toward Jupiter. But then as it left Jupiter, it should slow down by the same proportion that it sped up going in toward Jupiter. The way the slingshot effect works is, it's true, all that is true, but Jupiter is moving. Jupiter is moving through the universe at a much faster speed than our little rocket is. So what happens is, as the rocket comes into Jupiter, Jupiter's velocity sucks it along with it and picks up its speed as it slingshots out past it. The best way I could do it is picture a big fat elastic band on the back of a pickup, and you're riding a bicycle perpendicular to the velocity of the truck. And as the hook of this big elastic catches you, and the truck is going down the road, it grabs onto the bar of your bicycle and pulls you up to speed of the truck, and then releases you. Well, yeah, you're going a lot more at a lot higher speed than you were before, even though initially you were going perpendicular to the direction of the truck. So it pulls you along in the direction of the planet, and it increases your velocity dramatically. And that's how, the only way we've been able to achieve these higher speeds is using the slingshot effect. Now, we are moving at 18 miles a second. If an asteroid, and we'll get into asteroids in comments, if an asteroid were to hit us, it would probably hit us at 46 miles a second. That's about the average. Now, let's look at that. Remember at the beginning of the lecture, I said that the energy, the destructive energy, goes up as the square of the speed. At asteroid speeds, the same weight of object would do 3,000 times the destructive force of shooting at the velocity of a 220 Swift. And those of you that have had firearms experience know what a high velocity, relatively high velocity rifle will do. Well, this would hit with 3,000 times more energy than that rifle bullet. All right, again, I want to talk a little bit to give you a sense of proportion on speed. Light and electricity, on the other hand, dwarf even these speeds. For example, picture people in a 150-foot big auditorium. Not 150 yards, just 150 feet, maybe 3 times as big as this. And there's a speaker up there with a microphone like mine. And my words are then sent via satellite to people in Australia, opposite side of the earth. And they were either in the front row or had earphones on. Do you know that they would literally hear my words before the people in the back of the auditorium here? The speed of electricity and light is so fast, that by the time the sound reached the back, electricity and light would be in Australia, clear as a bell. So that gives you a sense of proportion as to how far, how out of proportion things that we understand, like the speed of sound, are. To be able to go halfway around the world and not, in less time than it takes to, what it would take us to walk 15, 20 steps. All right, now I want to show you about black holes, and I want to show you another thing. How many of you have heard the term escape velocity? This is the escape velocity of Earth. This is the escape velocity. It's the most misused word, I think, where science has come into the general public's use. People think a rocket has to travel at its escape velocity. Now, it's 6.8, the escape velocity of Earth is 6.8 miles a second. You don't have to travel at 6.8 miles per second. You could travel at 6.8 miles an hour and still escape Earth if your rocket just kept propelling you up and up and up and up. Escape velocity means what velocity would you have to fire a missile at or a bullet at from Earth and not put any more energy into it and still have escape from our planet. And for Earth, it is 6.8 miles a second. Now let me go and let's have the next slide. What you have to understand is that as you shrink something down, as long as you keep the escape velocity goes up by 40%. So gravity depends on mass and distance. So does the escape velocity. To escape from the sun, instead of 6.8, you'd have to go 385 miles a second. If you crush our sun to half its size, the velocity goes up 40%, even though the mass is the same. Now squeeze the sun again by half, and it goes up to 770 miles a second. Okay, now when a star reaches that neutron star that we kept talking about, now the escape velocity is half the speed of light. So you see, it takes a lot more. And remember, a photon of light is more like a bullet from a gun. If you went down and you squeezed it into a black hole, now the escape velocity is the speed of light, and so nothing can escape. So a natural product of a shrinking star further will eventually, you will reach the escape velocity of the speed of light. And that explains how a black hole works. The escape velocity, what it takes to get away from its gravitational fields. The rifle, you'd have to have a rifle bullet that fires at the speed of light. And up until comparatively recently, we felt nothing could exceed the speed of light. That would take a rifle bullet that fired faster than the speed of light to escape from a black hole. So that's how to think. A lot of stuff about black holes will make sense to you if you realize that it is simply a gravity so strong that the escape velocity is the speed of light. Okay, now that has to do with speeds, and I'd like to go on and do energy and power now. These are all elements that affect us in the universe. And let's change the slides now. Okay, how much energy is there in a kilogram, 2.2 pounds of mass? If you converted it by Einstein's equations, and I did it for you, you don't have to do it, and there will not be a quiz on this. If you converted it into energy, it's 9 times 10 to the 16th. A trillion is 10 to the 12th. So this is 10,000 times a trillion joules. And a joule is a relatively large amount of energy. Now, the world's energy consumption in 2001, everything that we ever did, was 36 times 10 to the 19th joules, or about 4,000 kilograms. In other words, when we did all our burning, all our fuel, all our atomic energy, we converted the mass of about one elephant into pure energy. That's how much energy powered all of Earth in 2001. Now, you'd say, you know, that's pretty impressive. I mean, to convert all that energy, all that mass into energy. Now, we're generating a lot of energy until you realize that this is what we did in 1 year. The sun, our sun, converts 100,000 elephants a second into energy. 100,000 elephants in 1 second. Now, you'd say, now you're talking some energy. Well, there are stars out there and pulsars out there that have this ratio to our sun. You take a policeman's flashlight, a 4-cell D-cell flashlight. Our sun is to a pulsar in energy as that flashlight is to our sun. So all our energy consumption is so minuscule compared to like what a pulsar would have, and even then they believe there are sources that would make pulsars go away. So that's how much energy is out there in the universe. And the only reason it isn't frying us, of course, is that it's so far away. Thank God. Okay. Something a little closer to Earth. The Saturn rocket, powerful rocket, when it was launched, during the time it was firing, it was producing 4% of all the energy or all the power that was being produced on Earth. 4% was coming just out of that one rocket, which is pretty impressive, until you realize that if we were going to reach that nearest star that we talked about in 100 years, we wanted to reduce the time from 27,000 to 100 years, we would have to have a rocket capable of generating 400% of all the energy on Earth. In other words, everything on Earth, this would have to be 4 times as much and continuously fire for 1 year. And then it would build up enough speed so that it could reach the nearest star in 100 years. So again, Star Trek is nice. If they find a new means of transport, then, go ahead and concede it to them. But with what we know today, it isn't going to happen. Now, I'd like to go, since it's in energy and power, and go to the other proportion to show you how far away and small things are. How many of you saw that movie Contact with Jodie Foster? With the VLAs and the big dishes and they monitored the stars and everything. If you take the energy that's actually been achieved by every VLA in the world since we opened the first one and you added it up, the actual informational energy that we got from all of those VLAs from the stars that actually came from the stars would be less than the energy of one snowflake falling. That's how sensitive they have to be and how far away from us these planetary constellations are. All that energy and all the radio frequencies would be less than the energy of one snowflake falling. Now, again, I want to talk about, we talked about speeds, but I want to talk about the energy associated with speed. Here's a number that you can kind of remember. If you get something up to a speed of 2 miles a second, it will have the same energy for destructive force, if that's how it's used, same energy as if that same object were made out of pure TNT. 2 miles a second, that energy would hit with as much force as the same object at 2 miles a second. It would do the same destructive energy as if it were made out of TNT. Another way you might say this is that if you had a 130-pound person and you brought him up to speed, or a 130-pound object of any sort, and you brought him up to 2 miles a second, it would hit and devastate a building with the same energy that was delivered to the federal building in Oklahoma City. That's how hard it would hit. Now, why haven't they done it? Because we haven't been able to achieve 2 miles a second. Whereas an asteroid, and we'll talk about those, hits with about 45 miles a second. So it goes up as the square, so we're talking literally 1,000 times as much energy in an asteroid as the 2 miles a second of pure TNT, because of that square of speed. Now, have any of you heard of Tunguska, the asteroid that hit in Russia about 1907? Now, this is documented. They know this is what happened. The asteroid hit with 15 megatons, equivalent of a bomb of 15 megatons. It flattened 200 square miles. How big was it? It was about 65 yards across. 65 yards, about a little bigger than this room here. It hit, and it hit the air so hard and detonated with so much force that it blew down trees and wrecked things for 200 square miles. Now, I want to put some of these asteroid things in proportions, and I've been asked to discuss this. The largest explosion that man has ever generated ourselves, that we've actually produced, the Russians did, not us, and it was about a 60 megaton bomb, many thousands of times stronger than the Hiroshima bomb, 60 megatons bombs. Now, as you remember, back, I believe it was in 95, the comet Schumacher-Levy broke up into 20 pieces and it hit Jupiter. If one of those pieces had hit Earth, Well, let's just look and see what happened when it hit Jupiter. Let's look at a slide. One of these pieces out of 20, there's Earth. It blew a hole in Jupiter with the fracture lines larger than the diameter of our entire planet. It literally made a hole in Jupiter that you could put Earth into. That's how hard it hit. How much destructive energy, and this had between 13 and 20, how much destructive energy just one chunk of it had. Now, if one of those parts had crashed into Earth instead of Jupiter, let me give you this so I get it right. Let me give you the proportions of what it would have been like. It would have been the same as setting off the largest bomb we ever did, the 60 megaton bomb, every 5 minutes for 13 consecutive years. That's how much energy it would have hit Earth with. Another way to say it, it would have been the same as setting off a Hiroshima bomb every square yard over the entire Earth all at once. That's how much energy it would have delivered to Earth if it had hit us. Or perhaps something a little bit closer to man-made stuff is if all the countries in the world had decided to increase, everybody that had nuclear weapons at the start of this year had agreed to make 10,000 times that amount of nuclear weapons and all detonate them at the same time, that would have been the energy delivered by one of the 20 pieces of Schumacher-Levy that had hit. Now, what effect would one of these pieces have on Earth if it had hit? Well, if it had hit in Dallas, the largest thing that was standing in the Midland area would be 2 feet. The shock wave would have been so strong that the strongest known materials that we have would have sheared above 2 feet. And of course, there's little warning. I mean, this thing is just going to come in, and it comes in so fast. As some of you remember reading in the paper, they didn't even spot an asteroid until it had passed us and was going away. So that's how strong it would have been. Now, if it had hit in Dallas, the shock wave would have passed through Earth in about a half an hour. It would have taken to pass through. And on the opposite side of the Earth, they would have had an earthquake of magnitude between 10 and 13. The soil would rise to over 700 degrees, and the air would be 2,000 degrees. Now, fortunately, there's a low chance of this happening. And, you know, they believe a smaller asteroid hit about wiped out the dinosaurs about 65 million years ago. But they have compiled your chance of a fatality from an asteroid, and if you want to change, we can go over that as an emergency. Now this is, and I'm just using that as our reference. Okay, the biggest chance of dying, which is a 1 ratio from an accidental cause, is an automobile accident. A homicide is 3 times that much. A fire is 8 times less chance, not 8 times more chance, 8 times less chance. An accidental shooting is 25 times, 1/25th the chance. Asteroid or comet is 1/100th the chance. But here's something that I thought: dying in an airplane crash with the average amount that the average American citizen travels is less than half the chance you'd die from an asteroid or comet impact. So you'd say, well, wow, if it's that much, and we have all these hundreds of thousands of people working in the FAA and in air safety, how many people do we have working in looking for asteroids and preventing this type of thing from happening? Less people and less money than we have working in a relatively large size McDonald's. We have fewer people than the employment staff in a relatively large size McDonald's, and we spend less money than that McDonald's would gross in a year. And the reason is that out of sight, out of mind. The chance of it happening in 1 year is very, very low. Well, how do we get these big numbers? Because if it did happen, the numbers would be so big. So when you multiply a relatively little chance by a relatively devastating force, you get a real life number. Think of a new way temperature. You know that molecules vibrate, and temperature is really to how fast these vibrating molecules bang into each other. That's what temperature is. So here's this one vibrating, and then the next one next to it vibrates, and when they hit each other, that's what makes temperature. So the reason that the stars are cool is because these photons prevent the collapsing star from getting the temperature, getting their molecules too close together. Now, we as humans can tolerate what, 200 degrees difference with the right clothing, and maybe with our machines 600 degrees. Well, the temperatures in the universe that we know about vary from zero, virtually absolute zero, to 6 trillion degrees. Way, way beyond, 6 trillion degrees. So in stars, the fuel that combines to come off holds the stars open, and once our fuel in our sun is used up, our temperature of our sun is going to go to about 90 million degrees from the 20 million that it is now. Man, under his most extreme conditions, can make a 250,000 degrees. We have actually had scientists make a 250,000 and sustain a 250,000 degrees, compared to what sits there in the center of the sun of 20 million degrees. And when the sun runs out, it's going to quickly go to 90 billion degrees. Let's have the next slide. And I want to sort of demonstrate how what makes a star shine is not what's heating the star, it's what's cooling the star. Okay, you see, as the molecules come in and combine, these photons come out. As they come out, they actually prevent the new material from coming in, and that's what keeps the star shining. 4 hydrogens combine to make a helium, and energy comes out. Now, the 4 protons that combine are 0.7% heavier than the helium nucleus. So the surplus mass is converted into energy, and that's all it is 0.7% is converted into energy by that one combination. And that's what still the sun consumes 100,000 elephants a second, converts into energy. Okay, now let's do, I want to move on to forces, and this is the 9th of the 10 subjects. Okay, let's deal with something that we know happened. Let's look at the next slide. 50,000 years ago, a meteor went into, and this is a computer-generated graphic reproduction of what happened. 50,000 years ago, a meteor hit in Arizona, making the crater there. The computed force at the leading edge of that meteor was 1,000,000 pounds per square inch. There is no known substance that can take 1,000,000 pounds per square inch. It pulverized everything. It literally boiled the Earth away, threw it up into space, and 200,000 cubic kilometers, which represents about 80,000 cubic miles of rock, burst into vapor and went up into space, surrounded the Earth, and while it wasn't as catastrophic, because this was just a tiny meteor, this one was just like 100 yards across, but it was made of metal, so it was more devastating. And that's the type of forces that we're dealing with. Now, I want to get into some strange stuff in forces. And there is a thing called the cosmological constant. This is a brand new discovery, brand new meaning 10 years ago. It turns out that everybody sort of knows what gravity is. It pulls. See, they were 4 degrees apart. Einstein said that gravity would distort space so that light will bend. The dotted lines are the rays of light with pure space. There came a time, as Einstein predicted, where there would be a full solar eclipse, meaning that the sun, the moon, we had a partial one out here, and the astronomy club went out, and we had witnesses and lectures on it and stuff, where the moon would block the sun's light, and when they looked, the light now had to pass by the sun, and it literally bent it from like 4 degrees to like 2.4 degrees. Why? It bent it. He said light would bend, gravity would bend light, would bend space, so that light thinks it's traveling straight, was actually bent through space. And everybody said, who was ready to ridicule the guy, when his equations came out right more accurately than their instruments could possibly know, they said, this man's a genius. Let's pay attention to him. And from that, our total thought process about space and time changed. Now they got the fourth dimension, they got all of this stuff, and we're still learning about that. Now, I'd like you to realize that, as you get out into space, gravity goes down, right? A 6-foot-tall man, if he had on his head a 10-pound weight, it would be 2/1,000,000th of an ounce less than at his feet, just because he's a little closer to being further in space. Now, if it was on the sun, it would be about 1/100th of an ounce, because the gravitational difference is so much stronger. Well, just when you start to think that's big, if it was a white dwarf, if the sun was shrunk to a white dwarf, it would be 10 pounds difference. In other words, it would maybe 1,000 pounds here, because white dwarfs are so strong. But on his feet, it would be 1,010 pounds. Okay, now on a neutron star, if you remember that neutron star, it would be 1,400 pounds difference. And on a black hole, at the event horizon, it would be 10,000 tons difference. And that's what they call, and some of you may have heard of it, particularly in science fiction movies, they like this name. It's called spaghettification. It would just stretch anything. With 10,000 tons of difference, anything is going to be stretched, long and thin. The forces and pressures are so great from some of these gravitational effects, something a little closer to home, that the pressure in the core of Jupiter, our own Jupiter, is 100 million times the pressure in this room. 100 million times more force in the core of Jupiter. It's so strong that hydrogen, something that we take for a gas, is literally crushed into a metal. It conducts electricity. It makes the crazy magnetic fields around Jupiter. If you look at the dot on the handout of the material that we gave you, just one period would have a weight of 7,350 tons. That's how much pressure is in the core of Jupiter. Okay, I'm going to move on to the last part, which is a relatively shorter part, and then we'll have questions for people that want to ask. The laws of physics as we know them and we're comfortable with, and I'd like to show you where they somewhat devastate and somewhat go apart. First of all, visible light represents less than 1/100% of the light rays frequency that we know exists. And who knows what's out there that we don't know exists and will discover. Now, we can't see past a certain point anything in the universe. And then let me explain why. This is kind of bizarre. If you take the universe as expanding, we know it's expanding by observation, it would be sort of as if you had raisins in a loaf of bread. Each one is flying apart from each other. Well, as you get out toward the edges of the universe, the raisins are flying apart so fast, and from us, say, toward the middle, it's flying apart so fast that they are leaving us at more than the speed of light. So if something left them, picture something being fired off the back of a railroad train that's doing 60, and you fired it at 40, it would still be moving away from you at 20 miles an hour. Well, now here's the interesting thing. Nothing can travel faster than light. We've always learned nothing can travel faster than light. But now we know that space can expand faster than the speed of light. So it is actually, at the peripheral of space, it's expanding faster than the speed of light. And I'm going to show you something else that you could do an experiment yourself to show something happening faster than the speed of light. So we have to get into with how Einstein thought about things. Let's go to the next slide. Here's the orbit of Mercury. It should just go around exactly the same every time, but it doesn't. Einstein was right. When we got our instruments in alignment and our thinking in alignment, the sun's gravitational field is so strong, so much stronger than anything we're used to, that it literally distorted space and time. So by the time Mercury got back to where it started from, space had moved. So it never could return to the same spot. So remember, even though we can't travel faster than the speed of light within space, it's sort of like water. It slows us down. Space slows us down. Space is proven to travel faster. Now let me show you an extreme case, and just to give you some examples of an extreme case of gravitational forces distorting space and time. Let's have the next slide. Picture an astronaut right at the event horizon. Okay, here's an astronaut falling into a black hole. Now, to the astronaut, if you notice, he's got a watch on. He feels like he's rushing into this black hole. I mean, he's being pulled in at terrific speeds. And his watch is running at normal time. Now, to people in a spaceship farther away, at a safe distance, that astronaut not only isn't falling into the black hole, he's not moving at all. He's frozen in time because the gravitational effect has distorted space and time so much. And his watch is not moving, not even a little bit. He's just frozen there. And they've had documented cases of things going into black holes that just sat there and didn't move. Now, something closer to home, which has been done and repeated, if you have two very accurate watches, I mean extremely precise watches, you leave one on the dresser and you take one in an airplane and fly that around the Earth in 24 hours and bring it back and put it next to the watch on the dresser, they will no longer be at the same time. They will be forever off time. Now, whether the watch that moved would be faster or slower depends on whether you're traveling from east to west or west to east. But since you had a relative velocity compared to the one on the dresser, forever from that point on, those watches, unless you reset them, will be different. The guy that worked out a lot of the theory of this said, you know, in theory, I guess you could, by flying in an airplane, you could extend your life, since by flying in the right direction, you could slow down time. He said, but that would be more than offset by the airline food. It would probably kill you early. So, and he's probably right. That was Stephen Hawking said that. Brilliant guy. Now, I'd like to, let's change the slides, and I want to show you, this thing may bring it home to you more than anything else, how far off we are. If you take a ship, an average speed ship, now sailing ship, but that's a pretty depiction. And an ocean-going boat relies on radio signals from the satellites. This is the GPS systems that you can buy. Well, do you know that if we use the original Newtonian mathematics, the original Newtonian theory, instead of Einstein's relativity, general relativity, that would be off. That ship would be adrift by a mile for every 3 hours of travel. If we had used the mathematics that we were learned in school about distance equals rate times time, and this travels this way, and so on, the things that make common sense to us in driving from here to Abilene or whatever, and we use that in our GPS systems instead of what Einstein said was right, proven fact, ships would be off by 1 mile for every 3 hours they travel. We've corrected it, got to give mankind credit for that. We have corrected it to the point where we can be accurate within inches now. And it all has to do with that little troublemaker Einstein saying that space and time distorted by gravitational fields. Okay, let me have the next slide. This is we're going to get into quantum mechanics. You've heard the expression before, the stuff that dreams are made out of. Well, quantum mechanics is really the dreams that stuff is made out of. These people, how they came up with this, it's incredibly amazing. Everyday stuff that would be impossible without the understanding of quantum mechanics is transistors, integrated circuits, televisions, radios, other than tube radios. All of this would have been impossible without the people that developed quantum mechanics. And I'm going to finish it off with something to show you how strange quantum mechanics is. All right, quantum mechanics says that this is the confusion. Light had always been thought of as little packets, as a guy throwing like a baseball, and that light was that baseball. Let's change the slide. So there's the baseball player throwing it, and we know that light works that way because we take baseball, we two slots, and it hits, and we can see every one that hits on this screen. Now, okay, so now we fully understand what light is. It'll work this way every time. Wrong. Next slide. Same situation, where we actually take the light, we run it through two slits simultaneously, and look at what it does. It cancels. What happened to the particle that hit here? Did it move? No, it didn't move. We can prove it didn't move. It just disappeared. That's quantum mechanics. It just disappeared. It went away. We don't understand it. And in fact, when a particle flies off another particle, there's a time schedule that we can predict millions of particles likely to do, but there is no way, no known way, unlike anything else, that we can predict when that particle will self-disintegrate. We can't predict it. It'd be the ultimate Las Vegas experience. You couldn't predict when it's going to happen. Now, let me give you the last example, and these are laws of the universe that are there. Let's do the next slide, and I want to take just a moment to explain this. And this is an example of how strange things are. If you have a quantum particle and you have an impactor, and it breaks this up. In quantum mechanics, nothing has happened. Nothing has even happened until it's observed. So by the process of observing it, you change the outcome. Not that you did anything, not that your instruments change it, just the fact that you observed it. So here comes a particle, an impactor, breaks a quantum particle into two parts. And it's always either a plus spin or a minus spin subparticle. Either the plus or the minus goes into the A box, and if it's plus or minus, it's got to be minus or plus. Now there's a sensor out here that at a distance x in the B, looking at the B box. And it senses nothing. It senses that there's something in there, but it doesn't sense whether it's plus or minus. Whatever it is, the opposite is in the A. When you observe, when you open it to look at what's A, in A, instantly, way faster than the speed of light, instantly the sensor picks up the opposite in B. What did our observing it have anything to do with B down here? Nothing. Yeah, but wait a minute, it affected it, right? But what did it have to do with it? Nothing. And I'd like to close with a statement by Niels Bohr, who was one of the leaders in quantum mechanics. And this is what he said. Anyone who is not shocked by the results of quantum mechanics wasn't listening when it was explained. And you know what? The newer laws we're discovering in quantum mechanics are even weirder. And you'll be reading about them within months in the newspapers. So it's a whole new world. You'll be reading about stuff going faster than the speed of light. And so maybe Star Trek isn't that far off. Maybe we'll be able to move through space and time in the quantum field. But for now, it goes back to what he said. Anyone who is not shocked by not only the results of the quantum mechanics, but what's going on in the universe wasn't listening when it was being explained. Thank you.
Thank you, Chris. Thank you, Chris. Now, if anyone will please look down toward the floor for a minute, we'll bring the bright lights up because it's going to be quite a shock. So look down toward the floor for just a moment.
Oh, you didn't? Okay. Okay, we're going to pass out a little thing of what was today's program, so that since the lights were out, we didn't think, and some cards if you want more information. The complete, I'll be happy to send anybody that fills the cards out and wants to my complete lecture notes that has just about everything that I said. It's all, and obviously it's free.
Okay, while these papers are going out, I want to tell you something you might be surprised to know. That crater he was mentioning over in Arizona, did you know that our Odessa crater is a part of that? The same object that created that crater over in Arizona hit in Odessa over here. And the great part of it is that the iron hit in Odessa. A rock actually hit in Arizona. We got the best part of it. And there's more than one crater over there. There's two of them. So we have a wonderful visitor center over there at the Odessa crater. So do stop by. If you're going out that way, exit 108 is the one you want to use. Exit 108.
We're not going to have enough of these printouts, so if there's several from a family, we'll just take one for a family and pass the others around. That way, maybe we can get them.
I will stick around after, or if anybody has any questions now on what my lecture was, or I'll stay after. It's your choice. Anything that you've heard about in the news that you thought, yes.
I just wondered where the black holes are in the Milky Way.
Oh, okay.
The question was, where are the black holes in the Milky Way? Well, we have since learned that the center of the Milky Way has a giant black hole. And the black hole weighs about 4% of what the whole rest of the Milky Way weighs. And there are black holes throughout the Milky Way. Now, what makes a black hole, who would want to venture a guess what makes a black hole hard to find? Yeah. There's no differentiation between what you see in a black hole, which has all the light sucked into it, and black space where there was no light generated in the first place. The way they know it is what's called lensing, gravitational lensing. And where they know now, if there's, for no apparent reason, light is distorted as it's coming toward us. So it's sort of like a mirage type thing that happens. And that way they can predict a black hole. And the computers are now getting good enough so that they can see the gravitational effects of a black hole on relatively distant stars. Say that star wouldn't move like that if there weren't a black hole this big over there. And how many of them there are, there's literally hundreds of thousands of black holes in our Milky Way galaxy. And some of them are tiny, some of them are very, very small. Because remember, you don't need mass to make a black hole, you just need force. Now one way to get force is mass, but there are other ways to get force. That's why I say it was a good science fiction story of a guy making a small black hole by force and just the whole Earth gets sucked in. Now he'd have to get away quick himself, but he just... Question. That's a good question.
There we go.
Oh,
I was wondering about the example with the astronaut at the Event Horizon. Is he actually there, or is it just you see he's there? Is the light coming towards you, like stuck there, or is it actually like his mass is there?
the best way to think about it is that his light is stuck there. Remember that you're going to slow the light down by the speed of the event horizon. Well, the thing is that if that gravitational force is strong enough to slow it down to zero, then it'll appear just to stand still for you. So that's why he's accelerating himself into it, but the light coming off him is being drawn back toward the black hole so that it has, in theory, zero velocity. So it appears just to be stopped.
And he's turning into a piece of spaghetti.
Oh, he's a long, tall guy right now. Yeah. The speed of gravity, you mean if something suddenly appeared, this is the best way to say it. Speed of gravity is the same as the speed of light. In other words, if a very massive object could be put at, those of you that, how many know how long it takes light to get from the sun to here? Yeah, 8.5, 11, let's just, again, the idea is not to make physicists, but yeah, it's minutes. But if all of a sudden, gravity, the sun doubled, same size, but doubled its density, we would feel nothing for 8 minutes, and then all of a sudden we'd be just drawn into it. Right? Or is that something different than you were aware of? No, that's what it is. No, that's right.
Come on, that is.
Considering how fast these asteroids are coming through space, is it reasonable to think that our observation ability is such that we could have 100% coverage and detect an asteroid coming into our gravitational field?
Yes. The way it happens is because they're moving so fast. What you do is you take repeated pictures and you subtract one picture from another. And the only thing that has moved, the only thing that's different from a picture you take every second, in this case it would be more like every hour, the only thing that's different is the picture of the asteroid. Then you run those into a computer and you say subtract this picture from that picture and show me what's different. And the only thing that's different, not the stars, not the planets, they don't move that fast, is an asteroid. And that's the way it's done when it's projected.
But that's the way it's done. But then is it possible to take that many pictures of our gravitational field and interpret that many pictures?
It is with computers. What they do is they throw out everything that isn't the same, so they don't have infinite storage requirements. Only when they see something that they call to people's attention, when they see an actual difference, do they then run it through. It's sort of like, you might call it like these surveillance cameras that just erase and keep going until something clicks them and tells them to save this. There's certain patterns. Here's an interesting thing, that another question that I'm asked sometimes. Well, okay, so we see an asteroid that's a mile across coming on a collision course from Earth. Well, so what? What can we do about it? Other than maybe pray, you know? The answer is we don't have to do much. Thank goodness we don't have to do much. In fact, every one of you has been in an intersection where a 70-mile-an-hour 18-wheeler has roared through that same intersection. Now, why weren't you killed? You weren't there at the time that the 18-wheeler roared through that intersection. So we don't have to major deflect that asteroid. We only have to slow it. We're moving so fast. We only have to slow it down a tiniest bit, and we'll be out of the way by the time it crosses our path. So we don't have to do major, hydrogen bomb type stuff and so on. We just have to slow it down or speed it up. In other words, if it were going to hit at our trailing edge, we'd want to slow it down. If we're going to hit at our leading edge, as Earth came into it, we'd want to speed it up so it would go past us before and hopefully into the sun. So the technology is there, and the realization, and we're discovering 4% more asteroids every year. Every year we're finding 4% more. But as you brought up, space is big, and asteroids are small, relatively. But that's how that's working. And they can do a pretty good job. I've seen test samples of where they scour the sky, and they find things down to 100 feet across, just like that. But they just don't have the resources now to look through the whole thing. And they can go out to about, with what technology we have now, and if they wanted to fund it, I think it's $137 million, they can go out to 2045. They can predict anything that might hit us out to 2045. And then, of course, probably that would be good enough if it were right, and we could wait 20 or 30 years when the technology were better and redo it again. Not that we don't care about the Earth after 2045. Maybe 2145, we're all dead, so we can't. No, that's not the right attitude.
Any other questions? Thanks again, Chris. Again, thank you all for joining us tonight. Join us for some refreshments, and we'll convene our regular Astronomy Club meeting in about 15 minutes. You're welcome to join us. Thanks again for coming.